So it is a great pleasure to have Professor Larissa with us today. So Professor Larissa is a professor in the Guangzhou University, China, and she will talk about the CMB data analysis. So Professor Larissa, you can share your screen and start. So
Hello, everyone. Thank you for the invitation. Thank you for being here. I'm actually speaking from China, as mentioned. Here is already 6 p.m., so almost good evening for me. I will share my screen. Maybe, okay, yeah, sure. Can you see my slides?
yeah,
Okay, great. So today I'll be talking a little bit about the CMB. Sorry, I did not send the abstract soon enough,
yeah,
but
it is fine.
I will be talking a little bit about data analysis. I'm not sure how aware you are about CMB polarization, but I think it's moving. Okay. But I will try to explain a little bit, not too much, because as it was told me that you are all doctors and you all know about this stuff I'm talking about, I guess. So I will give you a brief introduction anyway. I'll be talking about the new ideas that we're having on CMB data analysis, what's we're going forward in the next few years. Mainly, what we have been thinking about CMB polarization data, since we have been doing a lot with temperature and we still have these other signal to explore, and it's very important for cosmology. So this is an overview of my talk. I'll give you a motivation, why to keep studying the CMB, that we have been doing this for quite a while right now, but we still have much more to do. The goal of this analysis, I will do a recap on the CMB. I'll talk about component separation, which is the main goal of my talk and the project that I have been working on lately. And it's very important, not only for the CMB, but also for other observables in cosmology, as for instance, 21 centimeter observations. So I have been doing component separation for both of these observations, and I think it is one of the critical points if we want to do cosmology. I'll be talking about the ABS method, which is the method that I have been working lately. Tests that we've done in temperature, tests on polarization, and then this new framework that we just released the paper on arXiv in the end of last year. And we're still fighting with the referee, but I think it's gonna work out soon. First of all, I would like to start talking about the universe evolution. Probably all of you know about the standard cosmological model, which is the model that we have been working on mainly in cosmology. Of course, we have alternative models, but this is the model which has very good agreement with observations, and we have been testing it against different observables for a long time. And the CMB being the main one of this. So the CMB is the earliest information that we can get from the universe nowadays that we know. It released in 380,000 years after the Big Bang, and we know a lot about the universe because of CMB data analysis. However, we know that the standard cosmological model faces some problems, mainly, of course, the dark sector, which I will not talk about today. It's also studying the CMB and also other observables like the 21 centimeter is very important for us to try to understand nature, the nature of dark sector, mainly, you know, dark energy, dark matter mainly, but dark energy I think is a little bit harder to fit in. But this is one of the problems that we have nowadays in the standard cosmological model. And another, I wouldn't say a problem, but something that actually we have to still probe is inflation. So we know that inflation is put in the standard cosmological model to try to explain some things that we observe, but yet we don't have any direct evidence for inflation. So one of the goals to study the CMB polarization is that it can probe inflation by means of the B-mode signal that I will explain later. So we can actually see beyond CMB and go further away in the past of the universe if we're able to study what inflation predicts. And one thing inflation predicts is primordial gravitational waves. So we can either measure probe inflation by the imprint of cosmological gravitational waves on the CMB, or by directly measuring gravitational waves, I think, which is a little bit more difficult, right? So the goal now is to try to probe inflation through the CMB, through the imprint of cosmological primordial gravitational waves in the CMB polarization signal. And why do we think we can do that, or at least we have the hope to do that in the near future? If we do not measure anything, I will talk about this possibility later. Of course, we have maybe to rethink a little bit about the standard cosmological model, or we can try to push funding and finances to pay some new experiments that would be able to measure directly these primordial gravitational waves. But one motivation that we have is that we actually measured gravitational waves recently, at least for me is recently, 2015, so a little bit more than 10 years ago. In the history of cosmology, this is very recent. And we finally measured these gravitational waves, astrophysical gravitational waves, due to the merging of black holes. But yet, it's something that we can then measure. And the Nobel Prize for Physics was given for this discovery in 2017 to Weiss, Barish, and Thorne. So that is one of the motivations that keep us going forward in this search for the primordial gravitational waves that could probe inflationary theories. Another important discovery, breakthrough maybe in astrophysics, was even more recent. It was in 2023. We had this paper from Nanograv finding evidence for a gravitational wave background, right? Astrophysical background. So once again, maybe for sure we are able to measure these astrophysical gravitational waves. So maybe we can also try to measure the primordial gravitational waves. We have many ways then to try two ways basically to probe inflation. So we can measure gravitational waves in different ways. We have these ground-based experiments which measure the first detection of gravitational waves, these astrophysical gravitational waves, and they have been measuring events not so in a very frequently, I can say. So the LIGO-Virgo collaboration and CAGRA also in Japan. So we have these ground experiments. We have space-based observatories that are being planned in the future also to measure these gravitational waves. We have the pulsar timing array, which was the way Nanograv had evidence for this stochastic gravitational wave background. So it's we have many different ways of measuring these gravitational waves. But when we talk about primordial gravitational waves, so it's a little bit more difficult to do this measurement. And one way, and the easiest way now we can think of, is by the imprint in the cosmic microwave background. So you can see in this chart here a little bit of these this that I just mentioned to you, so you have different observatories and different events happening in the universe, and we can finally measure these waves. So the main goal of future CMB experiments, or at least most of future CMB experiments, is to precisely measure the CMB B-mode polarization, which can probe inflation, because this primordial B-mode is related to the primordial gravitational waves. So I will do now a recap on the CMB. Probably all of you are aware what CMB is, so I'm not going into details of the CMB, but just for, we can start discussing all these observables of the CMB and what we can do with them. Let's talk a little bit about temperature. So temperature has been studied for quite some time, since, the first satellite that was launched, even before with these balloon-borne experiments. So we had measurements of the CMB temperature, and we also started analyzing this kind of data, starting with the satellite COBE, with these anisotropies of the CMB, which was, they also got the Nobel Prize for this discovery. So we have this map here on the right that you're seeing there, and this map is the temperature fluctuations of the CMB sky, that is related, of course, to density perturbations in the early universe. And we can do a map decomposition and write these in spherical harmonics, as you can see in this first equation. And by this equation, we can get the power spectrum. So the power spectrum, you can see how to the equation for the power spectrum below the last line in this slide. And we get the power spectrum by the spherical harmonics coefficients. And power spectrum is very important in cosmology, right? We have different power spectra. And in CMB is also very important. So we get a map in the sky, and then from the map, we get the power spectrum, the power spectra. And from that, we can, for example, estimate the cosmological parameters and do some cosmology with that. Okay, so this is the power spectrum of temperature, CMB temperature. You can see that the standard cosmological model, which is the lambda CDM model, it fits well observations, very well observations. So you see that the standard cosmological model is represented by the green solid line, and I think this is Planck data. So the Planck data are the dots, the red dots. So we have a very, very good agreement between observations and the standard cosmological model. So that's why, even though we have problems in the standard cosmological model, we keep using it. Otherwise, we don't have a better model right now to explain all the observations that we have and still explain dark matter, dark energy, and inflation. So we stick to that for now. Then another observable of the CMB is the polarization signal. So we know that the polarization signal happened there due to Thomson scattering in the last scattering surface. And so we have this polarized light that we can also detect, and we write them as the Stokes parameters. And then we can write the polarized CMB field described as this spin 2 and -2 field of a combination, a linear combination of Q and U. So you can see in the bottom of this slide the polarized field of CMB written as Q and U. But if you came along with CMB data analysis and you have read it, if you Can you listen to me?
Yeah, please carry on. It is audible.
Okay. If you read some CMB papers, and if you are interested in CMB polarization, you'll see that we don't write CMB as Q and U parameters. We write the CMB as we say it as E modes and B modes. Okay, so how we can transform from Q and U to E and B modes, which is much better for us due to the coordinates in the sky. So we have, again, this polarization field. We can rewrite it as these spherical harmonics, again, as we did for temperature. And then from this, we can get the ELMs and BLMs, which are the coefficients for this first equation. And then we use actually then this formalism to explain and to talk about CMB polarization. So we have these ELMs in the left and BLMs in the right. And then we can reconstruct this map from E modes and B modes. What is important for us now actually is the B mode. The E mode is also very important. We can get different cosmological parameters from the E mode power spectrum, for example. But E modes, they have been measured with quite a good precision since, I don't know, WMAP and now with Planck satellite. So the main goal of future experiments is not measuring E mode with the greater precision. This is something that's going to happen, but it's not the main goal. The main goal is to measure this B mode, because as I mentioned before, these B modes, they are related to the primordial gravitational waves that could eventually probe inflation. So this is all the power spectra from the CMB. We have the temperature power spectrum, as you can see, as the first curve in this plot. So you have the CMB power spectrum temperature, you have the E mode, EE mode, okay, so the outer spectra of the E mode, the second one from up to bottom, okay, and then you have the CMB B modes as the last one in this plot. What is interesting from this plot is to pay attention that we have then two curves for the B mode, right? So you have this solid curve for the B mode, which is secondary anisotropy from the CMB. So we have the B mode related to the primordial gravitational waves, and we have the B mode, which is related for the gravitational lensing. Okay, so the CMB photons, they come from less scattering surface. They travel throughout the universe until they reach us. But in the middle of the way, they suffer gravitational lensing, okay, from the potential wells in the middle of the way. And this converts E modes into B modes. And that's why we have B modes that we call secondary anisotropies from the CMB, which it's interesting, of course, but it's not the main goal here. The main goal here is to measure this primordial B mode, which is related to these primordial gravitational waves. And there is a parameter, a very important parameter in the model that can give us evidence for the existence of these primordial B modes, which is the tensor to scalar ratio. So today, I think that I'm not sure if we have an upper limit smaller than this one that I'm showing there, but today we believe that R, okay, is below 0.044. So it's a very low value. This is from 2021. So maybe, I don't know, we have a better upper limit now. I'm not sure. So this is for, it's a very, very, very small value. Okay, so we didn't find it in any experiment so far. There are other experiments beyond the satellite experiments, like ground-based experiments that we know are trying also to measure these primordial B mode. I can mention, for instance, BICEP collaboration, ACT collaboration. There's some of them around, okay, trying to capture this signal. But the problem is that measuring this primordial B mode is very challenging because the signal is very, very small. As I showed it to you, the upper limit for the tensor to scalar ratio is below 0.5. So it's very, very small. And we have different contaminants in the sky. So we have foregrounds, many foregrounds that we have to take care of them. For example, the galactic foreground. So our galaxy also emits a lot of B modes, as I can say, and then it can mimic the signal that we are trying to find in our data. So this is a big challenge. I probably you know this story, but I think this is very interesting to say because it shows us the importance of this kind of work. Because we doing this component separation and foreground removal in a pipeline of an experiment, right? The experiment goes from building the experiment, collecting the data, to doing cosmology. People doing cosmology down there, they are more prestigious usually, and regarding the people in the middle of the way trying to reduce this data and make something useful for cosmology. So I'm here to advocate for them and say that this is a very, very important part of the job as well, even though we are kind of ghosts. Because if we don't do our job well, we cannot do cosmology later on anyway. So this is a very good example of what happened some years ago. I think this was in 2013, I guess. I always talk about this story because I think it's a very, very funny story. I was doing my first postdoc. I was in Italy at the time, and they had this Morillon conference, very famous, and Bicep Collaboration was in the conference, and they announced that they had finally measured CMB mode, okay, and probed the inflation. It was everybody was very happy because this is, of course, a Nobel Prize discovery. But as you can see in this plot, this is the plot they showed, and this was the plot maybe in the paper, the previous paper. It was not published yet. It was only on archive, and they announced it before being published. Is that you can see that they measure these dots, okay, the black dots. And if you draw the model for R equals 0.2, it's exactly what you would expect for the B mode, the primordial B mode for the first bump, and then going up for these gravitational lensing for the CMB, right? So when you look like that, it really seems that they had measured the primordial B mode. But after a while, I don't know, a year later, some months later, cosmologists started to doubt this result because R was too big, okay? The tensor to scalar ratio being 0.2. If it was like that, maybe other experiments would be able to measure it, like, for example, Planck. And nobody saw this before. So people start doubting that this result was consistent, was real. And then in a joint analysis between Planck collaboration and Bicep collaboration, they found out later that this was actually foregrounds from the galaxy. Okay, so it can really mimic the signal. So another paper was published there in 2015 saying that this was foregrounds. So this is important. We have to remove foregrounds before we can work on cosmology or on CMB cosmology. So foregrounds, they are a big problem, and we have to do some foreground separation. So we have CMB back there, and then we have all things that can happen in the middle of the way, and we have also our galaxy. That it's it's the biggest contaminant that we have for that. And how can we do that? I think the most famous way of dealing with the foregrounds in the CMB is using internal linear combination, or as it's called, the ILC method, which was the method used by WMAP and Planck. Okay, so we have a multi-frequency experiment. Here, for instance, I'm showing Planck. So we have from 30 gigahertz to 857 gigahertz. And then we can combine all these maps. You see that the foreground is very heavy. Galactic foreground is very heavy as we go very high in frequency, which is all this red blurry thing in the map. And we can remove it by combining these maps. Okay, so again, you can see these equations. So the first equation means then we have these coefficients from the harmonics, the spherical harmonics, okay? And then we can decompose it in different contributions to the CMB. So then we have the first contribution there, ALMC, which is CMB, and then ALMF, which is foregrounds, and then the noise, okay? And then from this, we can get the cleaned ALMs, which is the cleaned map from the CMB, doing this combination, okay, this internal linear combination. And then you can follow from these equations. We can get this weight for the maps just using the power spectra and the cross spectra from the different observables. Okay, so that's how different frequencies. Okay, so you combine this power spectra, as you can see in the first equation in the last line. And then this is the main methods that we have been using to do this work for the CMB, and the variations from ILC. So the ILC is the main one, and you have many variations of it. You can do ILC in harmonic space, you can do ILC in pixel space, you can do ILC in needlet space. So we have been rearranging this method in different ways, and we have been testing it and comparing with one another. Okay. And recently, not so recent, but recently, my friends from Shanghai, they developed this new method called the analytical method of blind separation, which is very interesting because it is not in the map space, okay, in the pixel space. It only deals with the power spectra. So because of this, the method is much faster and faster and simpler than the ILC in many ways. So this is one advantage of this method, and then I started working on that. So here, the first equation that you'll see there is this very similar to the equation you saw for the ILC, right? But here is just the power spectra. So IG obs is the observed power spectra in these frequencies, I and J. I think this is J, yeah. So you have CMB plus foregrounds plus noise, okay? And then from these, you can get, from this matrix of power spectra, you can calculate eigenvalues, eigenvectors, and finally obtain the clean power spectra of the CMB. So this is some details of the method. I don't think I can get through it because as I can see here, we only have 10 minutes more. I will pass this time a little bit. But okay, let's not get into details of the ABS, and let me show you the results of this work on the ABS. So let's start with the temperature. So first, this paper that you can see there, you can find on arXiv from our friends from Shanghai. So we simulated 7 frequency bands as Planck satellite, okay? And then we added some foreground components. So this work was done all using simulations. So we add the main ones for temperature, so synchrotron, free, thermal dust, and anomalous microwave emission. And each one is important in a different frequency band, as you can see in this plot over there. So, and CMB is mainly, you know, the foregrounds mainly dominate the CMB signal in most of these frequency bands. And you can see this statement here in these plots. I don't think it's so simple to see. It's a little messy, but you can see 44 gigahertz, 70, 95, and all the frequencies that we're working on. And you can see that the CMB is the blue curve. Okay, so the dark blue curve is the CMB. You can see that in most of these plots, CMB is dominated by one foreground at least. Okay, so you can see that just by following the colors. But here is our recovery. So we use the ABS method on full sky, and we recovered the power spectrum, the CMB power spectrum, T power spectrum, temperature power spectrum, with good precision. So you can see that the CMB, the model is the standard cosmological model is the real CMB is the red one, okay? And the recovered CMB, the real CMB from our map, input map, compared with the recovered CMB from our method after doing the component separation, okay? When we included foreground and everything. So you can see on the left panel, which is full sky, and then the right panel is also full sky, but in this case, we added a very, very high synchrotron signal. So just to make sure that the method is good enough to remove the foregrounds, even though in this very extreme situation, okay? We also tested against galactic mask, so we avoided the region where the galactic foreground is more intense, there in the middle. We just used the simple mask, just removed the pixels in this region, in this stripe that you're seeing there. And again, only in 150 gigahertz CMB is above the foregrounds, okay? You can see in the power spectrum below. And here again, you have the comparing the galactic plane cut, the results for the galactic plane cut with the results for full sky. So it works well if we consider CMB temperature. So this was the first test that we did for this ABS method. Okay, so we did 50 independent realizations to test for this ABS, okay? And the power spectrum fits well within 1 sigma aerobars at most scales. So it was a good test. But then we have to move to CMB polarization, because that's the main goal of future CMB missions. We have been dealing with a lot of possible missions for the future. The main one that is already, it's going to launch, which is Lightbird from Japan. So Lightbird, it's there 2027. It's not gonna happen. Maybe in the next 10 years. Lightbird will be launched 2032, 33, something like that. That's the expectation for Lightbird, I think. So it's a primordial beam mode mission. It's the main goal, okay? So to measure this large-scale CMB polarization, and Lightbird is going to happen. So this is our, our hope for the future. Also together with the ground experiments, the ground-based experiments, because the other ones, they are yet not gonna happen. They are just an idea, okay, just a dream. So PICO from NASA and CORE from ESA, they are just dreams so far, okay? They're not being seriously considered right now. So just Lightbird. And if we, for instance, cannot measure the CMB B mode in Lightbird, primordial B mode, so I don't know what's going to be the future, because if we don't measure anything, not even a hint, I think it's going to be difficult to find funding for other experiments in this direction, even the primordial gravitational wave direct measurement. So we did this experimental setup. So we mimic an experiment like PICO, okay, in this to test CMB polarization, because for Planck, of course, it's not possible. The sensibility of the experiment is not good enough. So we added two main foregrounds for polarization, which is synchrotron and thermal dust. You can see also in the plot. And in this case, of course, the foregrounds are much above the signal. So you have CMBE as the blue, the light blue curve. And then you have CMBBB, the shadow, gray shadow, very down the plot, okay? So you have R equals to 10 to the minus 2, and then R equal 10 to the minus 4. So you can see that foregrounds, they play a very, very big role in the CMB polarization, especially if we want to measure B modes. And we saw that also with BICEP. So for this test, we used, as I mentioned, the foreground, synchrotron and thermal dust. We simulated it using the PySM. That I don't know if you heard about, but PySM is available, publicly available, okay? And then we added instrumental noise, but very like Gaussian instrumental noise, uncorrelated from pixel to pixel and from channel to channel, okay? So very ideal simulations, I must say. We also use the mask to avoid the galactic foreground, the more intense foreground, which is in this region, blue region in this mask, okay? The blue region is the pixel that we are removing, the pixels that we are removing. So it's final area of roughly 75% of the sky. But when we do this, we introduce a big problem, okay? So when I showed you how to convert from Q and U to E and B, it's simple like that, just when you use full sky. When you have to do this in partial sky, it's not so simple. So we cannot decompose Q and U into E and B, okay? In partial sky in this simple way. So we have to use some very different methodologies to do that. And this introduces a lot of errors, including the E2B leakage. I'm not gonna show you how we do that, okay? So I don't know if you are unaware of how this is done. You can talk to me later if you are interested in this topic. But we use the methodology from Zaldariaga. It's Smith and Zaldariaga. You can find their paper to try to do this decomposition into E and B in partial sky. But we had a lot of problems, especially we also found this paper later from Ferte that especially when you use masks with holes, the performance of the method deteriorates a lot for multipoles below 100. And this is a problem because what we want to measure is exactly in large scales. So I don't know if you remember the plot that I showed you, the power spectra from the CMB, all of them. When we are looking for the CMB B mode, we are very interested in this very, very large scales, okay? And if we have a method that cannot recover well these large scales, so it's a problem. And then we also have biases in the component separation techniques, especially in large scales. So it's a very hard job. I'm not, to be honest, I'm not sure if we're going to measure anything at all. But yeah, we have to try. So this is the full sky results for the E mode on the left and B mode on the right. You can see clearly for full sky that we have very, very big error bars in large scales, okay? So for R equals 0 with no gravitational waves at all, no primordial gravitational waves, and R 0.05. So this paper is from 2021. So the upper limit, it's still a little bit above the one we have now, okay? So, but we still see that, you see that we have big error bars in large scales. So I don't think it's very well suited in this form to try to really recover the CMBB mode in large scales. And then here's the result for partial sky. It's even worse. As I mentioned, for partial sky, we have messed with holes that make the methodology, especially the methodology for decomposing E and B from Q and U, deteriorates fastly for else below 100, and then we want something below 50. So it's not well suited. So we found in this paper that the ABS is able to estimate E modes and B modes, but not in the scales we desire, right? Not in the multiples that are important for this B mode detection, okay? Not for full sky, not for partial sky. So in order to do that, we have to improve not only the methodology, the component separation methodology, which is the ABS, but also we have to improve the decomposition in partial sky. Especially if we want to deal with the ground-based experiment, which is, we have no choice, right? We just have part of the sky available. So the advantages of the ABS, one of the main advantages, it's a blind foreground separation method. We do not make any assumption about the foregrounds, but this is also the same for ILC methods, okay? But one good thing that it's the most important for us is that the ABS is very simple and fast implementation, and you'll see now why this is important and what we can do with that, okay? Now in the end of last year, okay, November 2025, we released the paper on arXiv, proposing this new methodology for estimating cosmological parameter using machine learning. And this was possible, this full pipeline, this full framework was possible because we used the ABS as the component separation methodology in the pipeline, okay? So we know that when we do machine learning, we need a lot of simulations. And to do that using, as for instance, the ILC method is very complicated because we cannot, we don't have the power, the computational power to do that. So for the ABS, we could do that. So we could estimate for light burden, for Pico, and here you can see in these two plots on the top that we have very good recovery for light bird and for Pico, okay, for the B modes on the left and for E modes on the right. For different, for our different cosmologies, different values of R and of the optical depth that we also tested. So Lightbird is going to launch. So it's important that we have methodologies that we can compare with the traditional ones that are already in the market for a long time. And these new methodologies that using different ways of estimating the cosmological parameter. And for our knowledge, that's the first time that we are combining machine learning directly with this component separation technique, okay? Because it's very prohibitive due to the long running of the codes and all, okay? So we use, I just make a very brief introduction of what we did. So we use a set of 10 recovered BBE spectra for each of the 500 plus 200 cosmologies, so pairs of R and optical depth of tau. So consider for our simulations. So we split the first 500 into 400 and 100 cosmologies for training and validation for the neural network model. And that's our result. So it's like work in progress, but it's done. Finally, I think it's going to be published soon, we hope. So we have here that, of course, we see that for Lightbird, we don't have as a good recovery. The light bird is not here, but the light bird is the blue line, and the orange line is for Pico. Of course, for Pico, we have a better recovery because it would be a more sensitive instrument, but we still can recover for light bird the tensor to scalar ratio in as you can see there, and it's we are in agreement with the latest results for the forecast for light bird. Actually, this was all this work was discussed with Lightbird collaboration, so maybe it can also be used in the collaboration. So here in the left, I put for you some maybe important things for the machine that we use to do these runnings, because we need a powerful machine, but we could do this and test in a few minutes, which is awesome. So the goal of this paper was actually not the forecast, okay? So it's to introduce the method, say that we finally can unify a component separation technique with machine learning to estimate cosmological parameters in a fast way, in a feasible way. And we can, of course, then use this in different experiments to validate and compare with other methodologies. So I think that's my conclusions. Thank you for listening, and I'm open for questions.
So thanks a lot. So now it is the time for discussion. Yeah, please, questions and queries if you have anything.
Good evening, ma'am. The data is accessible, CMB data, right now, means yeah, on any GitHub file or archive.
I didn't get the question. If we have any CMB data right now?
Means
Mohit, can you be louder?
Yeah, ma'am. This CMB data is available on any GitHub file or to access.
And so in our paper, or in this series of papers that I showed you, we just used simulations. We didn't use CMB data. From satellites, of course, the last data we have is from Planck, so we could test it, the Planck data. But as I mentioned to you, Planck doesn't have very good sensitivity for polarization, so we could not do that for polarization. There are other models, other experiments coming up soon, ground-based, but yet we're going to have problems for doing this decomposition, right? So we have BICEP is releasing data, and we have the Chinese experiment I didn't mention, but the picture in the first picture from the talk is from the Chinese experiment called Ali CPT, which is in Ali in Tibet, the city, and the main goal is also to try to measure CMB B mode, primordial B mode polarization. So probably maybe we're gonna still have some light of Ali CPT this year or next year. So yeah, we have other things going on besides Lightbird, but the ones I mentioned here, they're just simulations.
Thank you, ma'am.
Yeah, Sayantan, you can go ahead.
Sure, ma'am. So I was actually first asking that I think after this that fiasco with the bicep 2 about the HK modes, I think now there is a Siemens observatory at Atacama, right? I mean, the scanning the southern one. So I'm just asking that what is that, because I mean I actually listened to Brent Keating's talk quite a long back. I mean I think the target was to reach R equals to 0.01 or something with 5 sigma or something. So I'm just wondering that I mean in the CMV I think you have only taken northern sky. I mean even the simulated data. So is there a cross correlation possible? That is my first question about the Atacama deserts one. Yeah, Siemens observatory.
I don't have updates on Simon's observatory, but I think it's very optimistic to say that you're going to measure R with 0.01.
No, I think that was the yeah. No, I think that was the like tagline. I mean, I don't think they have done it, but yeah.
No, I think it's very, very optimistic. I don't think even Lightbird is that optimistic about these numbers. So I don't have the update on them. Yes, we could try to test, implement all this pipeline also for Simon's Observatory. But again, my biggest concern, my biggest problem is partial sky analysis. My framework that we released now, this is a future work. Okay, the referee also asked about that, but I think this is a next step for my students.
I see.
It's work on partial sky because this is more complicated, and we need the way it is now. It's not possible.
Yeah. The reason why I am a little bit interested from a theory point of view, because just like in primordial power spectrum, I mean, they are non-Gaussianity, the 3-point correlators are important, right? So here also, like, I mean, EEB modes, and this gives a very strong constraint on the inflationary model, right? I mean, that's it. So I'm just asking that, have you any plan for doing that? I mean, like the optical bispectrum analysis or the EEB modes, etc. Like, I mean, there are certain templates which you can rule out, right? I mean, without directly observing the B modes. So could you have some comments on that? I mean, yeah, thank you.
Yeah, it's true. It's another way of doing that. Yeah, trying to find non-Gaussianities. No, I didn't work on that. I was just working on this for foregrounds actually, but not looking in the CMB. But I think in this case, you need a map, right? You need a clean CMB map. For instance, in my framework, we just have power spectra, so we don't have the map. So we have the advantage of being fast, but we don't have the map. For the map, you need the ILC, for instance, or any of these variants of this component separation methodology, and then you have to do the standard way, right? For estimating parameters and getting a map, and then from the map you can try to look for these non-Gaussianities. But with the power spectrum, you can do that.
So maybe just a running question on that respect. So I'm just curious that in case the full sky analysis is not available, like because when we do the 3-point function, etc., we do the full sky analysis. For partial sky data, I mean, could you still use the templates, or like is it a wrong analysis? Like I have the partial sky data, and I am using the CMB templates for the finding the non-Gaussianity or something like that. Is it a correct way of doing it, or is it a wrong? Because I am definitely missing a lot of L. So just curious.
I think you can do, but you have to take more care. Like, for example, every time we use partial sky, we have to take care of different things. It's not so direct, So partial sky is complicated. That's why I think it's gonna be very hard, very, very hard to get any measurement, any like real direct evidence or indirect evidence from ground-based experiments. It's like they are like pathfinders, in my opinion. They are there for us to learn the methodologies, learn how to do it, try to do our best, but I think it's very difficult to get anything from this data.
Yeah, sure, because there is almost every other day there is a high energy paper on the full sky analysis of the non-Gaussianity. Sure. Yeah. Okay, thank you, ma'am.
Okay, anyone else?